I will start by introducing you. So it is a great honor and pleasure to have with us today in our seminar, Professor Aina Puce from the Department of Psychological and Brain Sciences at Indiana University in Bloomington, Indiana. Professor Puce did a Bachelor of Applied Science, Biophysics and Instrumental Science, and a Master's of Applied Science in Physics at the Swinburne Institute of Technology in Melbourne, Australia, and then continued to do a PhD in medicine at the University of Melbourne. She then did a postdoc in neurosurgery at Yale University School of Medicine. Professor Puce held multiple positions and now holds an endowed professorship as the Eleanor Cox Riggs Professor in the Department of Psychological and Brain Sciences at Indiana University. She has served as the Deputy Director for the Brain Sciences Institute at Swinburne University in Melbourne, Australia, as the Director of Neuroimaging at West Virginia University School of Medicine, and as the Director of Imaging Research Facility at Indiana University. She has supervised dozens of students and postdocs, many of which now hold research and faculty positions across the world. She has given many invited talks in international meetings across the world, has been on many international meeting organization committees. She has more than 23,000 citations and an H-index of 51 according to Google Scholar. She has published multiple scientific studies in top leading journals as Nature Neuroscience, Trends in Cognitive Science, and others, and also book chapters. She also served in multiple editorial roles and until recently was the senior editor of the journal Neuroimage and an associate editor of Perspectives of Psychological Science. Her research focuses on the neural basis of social cognition, which is the ability to interpret the actions, intentions, and emotions of others. She uses multiplicity of methods, including behavior, EEG, fMRI, event-related responses, eye tracking, and white matter tractography, as well as MEG studies via collaboration. So without further ado, I'd like to welcome you, Aina, to our seminar to hear about your research, and thank you so much for joining us.
Thank you, Sharon, for that lovely introduction. And I feel a bit intimidated because after last week's tour de force by Jim Haxby, that is just really hard to follow up. So I'm going to do the best I can. I'm going to have to do the best I can. So let me share my screen and let's get started. So what I'd like to speak about today is a recent study that was a collaborative study that took a lot of people and a lot of effort, and which I was able to work on while I was on sabbatical. Thanks to Indiana University, I spent a semester in Paris in the lab of Nathalie Georges, which I'll tell you about in a minute. And so that's what made that work possible. So I'm very grateful to my university for giving me that opportunity. So speaking of my university, this is just some shots of our campus at different times of the year. And right now, of course, I was telling Sharon that it's quite cold. There's no snow on the ground, but it was -8 yesterday morning when I had to walk across campus. Not a fun time. We are, of course, crazy mad for football and basketball, and we're now entering that madness of the season. But we also have a wonderful music school in our institution. It's one of the best in the country. It's the Jacobs School of Music, and it vies with the Juilliard School in New York for the title of the best music school in the country. So we are always able to go to multiple concerts and recitals, and it's just a joy to live in this area. Okay, before I start my talk, I just want to acknowledge funding sources. Before I forget, this work seeded and continues, and we're continuing it, seeded a grant for a joint grant, NIH on our side of the Atlantic, and for Nathalie Georges and Max Chamon in France. The investigators on the French side for this study were covered by some infrastructure funding from Investissements d'Avenir from their local national French scientific body. We had a neurologist on the project. Vera Dinkelacke was funded by the John Boast Foundation in France. And of course, I've already mentioned and acknowledged my university. Okay, so the roadmap for today's talk, I want to just describe the rationale and reasons for why we did what we did. Talk about methods, of course. Spend quite a bit of time on that, and lots of results to show you. And then I'll do a summary of that. And then I'm going to talk a little bit about outstanding questions, because this work and some other more recent work by others that I'll mention raises some interesting questions to think about. And in fact, things that I've been thinking about for 20 or so years. And I'm really glad to see Rafi Malak in the audience, because I'll be interested to hear what he has to say. So let's talk about why we did what we did. We were really after trying to examine information flow within the face processing system. And that it can be done, of course, in many different ways. People looking at fMRI studies and non-invasive neurophysiology and functional connectivity approaches and network science approaches. We took a slightly different tack because I'm a believer in multiple methods and converging evidence from different modalities. And so this was our attempt to try and think about things in a slightly different way to what had been done before. Okay, so let me guide you through the madness of this study. On the top here, I'm representing the face processing system in the human brain, and the literature divides it into a core and extended system, first proposed actually by Jim Haxby. So he did a lot of hard work with Ida Gobini in a review article, and so they've split the core system into essential structures such as the fusiform gyrus and parts of the occipital cortex, as well as the posterior aspect of the superior temporal sulcus. And then there's an extended system that deals with other functions that are important to face processing, but aren't the essential elements of it. That's shown in blue. And there are multiple areas, particularly here on the medial surface as well, including the amygdala, that are important for taking the information from the face and looking at things like identity and expression and so on. And then the question is, how do these areas talk to one another? And so this is this next cartoon here is one that's adapted from Cullinan Grill Spector's review of 2017, showing elements of the core and the extended face system. And I've modified this a little bit, but the lines, the solid lines between these areas, these brain areas, which includes other areas such as primary visual cortex and an early visual area, as well as the intraparietal sulcus. These are joined by lines that indicate a known white matter connection that's been established between these regions. And so that's great. This is wonderful work by many people, including people in Cullinan's lab, but there's a lot of work to do here. we, for instance, we have an essential part of the core phase system, and we don't know how it connects to these other parts of the pathway. There are other really important parts that are involved in identity and also expression analysis. But we don't know, for instance, how the amygdala and in social attention, how the amygdala fits in this picture. And the same with the posterior STS and temporoparietal junction, which is incredibly important for mentalizing, and it's part of the mentalizing network in the human brain. So there are lots of question marks here. So what we tried to do in this limited study was to try and get rid of this question mark here. How does the posterior STS communicate with the fusiform gyrus? And the reason why that question was so important, at least to me, is that there is no known anatomical connection between the two, direct anatomical connection between the two. So how do they talk to each other? And so that's what drove this study. This is not a simple question, because when you look at the posterior brain, human brain, and the white matter pathways that exist there, this is a real tangle of pathways. And I take this figure from our paper, but prior to that, it was published in Dan Bullock's paper on these white matter pathways and describing a method which he developed in Franco Pestilli's lab to differentiate between these various pathways, and which is a challenge, particularly around the back here. What he chose to do differently relative to other people was that he does the tract tracing, but he's also relying heavily on surrounding neuroanatomical landmarks as well, and so that's what made that possible. So that's work that he has published, and that's referenced in our paper that I'm talking about today. So that's the kind of rationale for doing this study, to find a link and what the nature of the link is between these two structures, the posterior STS and the midfusiform, and to try and work out how that link might happen in this, what I can only describe as schmozzle of white matter pathways. So we have this study that took us actually a couple of years to analyze. We analyzed in neurophysiology over the 6 months while I was in Paris with Mariana Baborebolo, who led this study. And of course, it was in the lab of Nathalie Georges. And so, but it takes a village to do science like this. And so we had collaborators on the French side, Laurent Hugueville, and of course Vera Dinkelacke, Vincent Lambrec, who's the neurologist in the program, Katia Leongre, who is an engineer, and Claude Adam, who's also a clinician in the Paris Brain Institute in the epilepsy surgery program at the Salpêtrière. And the white matter endpoint part of this project, I've already mentioned Dan Bullock, who was a graduate student who's now just finishing his postdoc in Minnesota, who was working in Franco Pestilli's lab. And Franco has a cloud-based data analysis platform called brainlife.io. And so Dan developed the white matter tract endpoint software for Franco. And Dan's software is available on GitHub if anyone's interested in that. All of the code is there. So we started off, of course, being open science practitioners, the code is available on GitHub, as I said, for Dan's work. And then we started off with a preprint, and then the paper was published a while later. And we also were able to get the cover art for the journal January issue based on elements from our study. And this is artwork that I did, which is kind of cool in a way, because it was 20 years ago. We did a large series of intracranial studies with Stuart Allison and Greg McCarthy. And that time as well, I did a cover design, which was accepted by the journal. So it's kind of coming the full circle. So that was, well, on a personal level, sort of quite meaningful to me. Okay, so let's talk about the methods. And if people want to ask clarification questions along the way, please do interrupt, and so, because I don't want to confuse people. Okay, busy slides, and I'm going to go through a lot of busy slides, so we're just going to take our time. Let me tell you about the data set that we worked with a little bit. It was an existing intracranial EEG data set with a face processing task, which I'll explain in a moment. And it was work that was led by Josephine Huygen in Nathalie Georges' lab. Josephine did a PhD, and she designed this task with Nathalie, and they were interested in looking at amygdala activity in particular. And of course, that's very hard to get in these epilepsy surgery patients that they were doing these intracranial recordings from. And so they, of course, recorded other data. And so Josephine did her PhD work on the amygdala. And so there was this data set that was there in Nathalie's lab that had not been analysed. The rest of it hadn't been analysed. So we took it upon ourselves to spend the time that I was in Paris with them to analyse the rest of that data set and mine that data set. We localised, of course, the intracranial electrodes based on MRIs, and that's their system at the Salpêtrière in the epilepsy surgery program. And then we took, because it was a task with multiple parts, which again I'll show you in a moment, we had to we epoched the data first into quite long epochs, which would reflect a trial because there were multiple stimulus types in the trial, and we cleaned them and also rejected epochs where we couldn't get rid of the artifacts. We started out with 18 patients, which we thought was a reasonable data set. But then as we started looking through the data and really sifting through the data, many of these patients had persistent interictal spikes. And by that, I mean epileptic discharges that were occurring between seizures, and they were quite persistent. And this makes sense because these people are they're being monitored for a seizure disorder, and their anticonvulsant medication has been withdrawn. So they're going to have that kind of activity. But in our case, we were also concerned about it affecting cognition and perception and cognition. We then therefore were very let me say, savage about rejecting trials with these kinds of artifacts in it, because it's not just the activity at the local site, the epileptic activity, but it can spread to other areas and influence other areas. And when we looked at the behaviour on the task, some of these people were compromised. They weren't getting as many correct responses as they should have been to a very easy task. So that unfortunately left us with only 11 people to analyze data from, which was not optimal, but we really thought it was better to have a clean data set. On our actual behavioral task, the face processing task, we also discarded trials or epochs with incorrect responses, and I'll describe that in a moment. And then we averaged data by condition for at each electrode site in each subject, and for the different parts of the task. We took the intracranial activity and expressed it as bipolar activity, and that allows us to make to discuss the activity as being more local and focal, to cut a long story short. And then, of course, we rechecked our anatomy for where the electrodes were, because what we then said was we expressed bipolar activity. You're taking activity between two contacts. And so we then took the midpoint of that distance between those two contacts to indicate the location for that bipolar activity. So therefore, we had to recheck all of the anatomy. Then what we did was, for that bipolar activity, we normalized the evoked activity. And this is really, really important to do, because when one does intracranial recordings, depending on where the electrodes sit, relative to the generators of the activity, you can, if you are very, very close to a generator, you can get very, very large potentials. If you are far away, you can get very small potentials. And so within each patient, we expressed all of the neurophysiological activity in terms of Z-scores. That levels the playing field, as we say, but also the advantage of that is that sometimes in some patients, the implants, of course, are different in every patient. Sometimes you might get an implant where the electrodes, just by chance, happen to be very, very close to the generators. In other patients, maybe not so much, so that when you combine activity from multiple individuals, one individual or a couple of individuals will dominate that sample, and there's a bias there. So that is why we normalized activity, because in everybody's activity is expressed as Z-scores. You still see all of the changes, and then we've got at least they've got an equal weighting if we do any statistical testing on them. So then we did, in terms of statistical testing, we had a couple of passes. We through the data, first of all, we took identified sites, electrode sites or bipolar locations, where there was our evoked activity had Z-scores larger than 1. Very, very low, very loose estimate, but that was the start. And then for those sites that were identified with that, we then did a cluster-based permutation t-test against 0 across time during the epoch at each site. And of course, we allowed for multiple comparisons. And then we visualized the activity as a function of ROI. And that's what I'm going to also explain, because that's a fairly complicated procedure. But that's the methods in a nutshell so far. So let's talk about the task itself. And this was, as I said, work from Josephine Huygen, who designed this task with Natalie. And so they had a multiple part task. Let me take you through it. The patient sees a fixation cross, which stays on the screen for a variable interval. The first, there's a stimulus that we designate face 1. This is the onset of a face. It's always a neutral face. It's always looking straight at you. And it's been taken from a set of faces that we had generated in the lab when I was with Greg and Truett. And so what they did here is they chopped out the hair from all of these faces. And so we've just got the oval of the face. After a variable period of time, the next stimulus comes along. It just replaces the first one. So it's an apparent motion kind of effect. And it looks like, at least with the gaze change that's there, it looks like there's the eyes suddenly look away. So let me just talk about the gaze aversion for a second. We have either on this face 2 that comes up, the gaze staying either direct at the observer, or it can avert to either the left or to the right. And so that's that's one of the conditions. The other thing that can happen is there'll be an emotion, and it'll always be a change from the neutral face. There's always an emotion. Those 2 emotions are happiness and fear. And so this example here shows a fearful face looking away. Now, all of the conditions, the emotion onset, whether it's a happy or a fearful face, whether it's left or right gaze aversion, or whether it's direct gaze, all of these are counterbalanced within the experimental design. We have a large number of trials. There was something like, if I recall correctly, 780 trials in that experiment. It sounds like a lot, but you have to factor in, we're going to reject data due to epileptic activity. We're going to reject data if people are wrong to the target task, which I'll tell you about now. But that's why we need extra trials. Every time you design a task with these patients, you have to provide extra trials. So then what happens is there's a third transition. Now, we didn't analyze that explicitly, and I'm not going to tell you about any of that today, but just for the sake of completeness for the task, so you know, there's a third stimulus condition that comes on. This face 2, stays exactly the same. And what comes on is a little checkerboard, which can come on either side of the face. And it can be congruous with the gaze, as is shown here, or incongruous with the gaze. And then they have us up to a second to respond to that. And so what happens is, on every trial, they have to respond with where the target is, whether it's on the left or the right. And then they're told, that's what they're told. And then we've also got some what we call catch trials where this target doesn't come up. And so then that is a kind of a monitor of whether the person's paying attention, whether they're doing this very, very simple task properly. And so, as I already mentioned, sometimes when in the presence of epileptic discharges, they don't do the task correctly. You have to keep these tasks simple with these patients. So that's the task. And so what I'm going to focus on here is the responses, the activity that's elicited to these 2 faces. And that's what I'm going to spend the rest of the time on. Before I do that, though, these are the 11 people that we studied and their clinical characteristics. There was a reasonable balance of male and female. They were all adults. Their handedness was mainly right-handed, as tested with the Edinburgh handedness inventory. This is when their seizures started in life. It was variable, but most typically, the kinds of seizures that are being evaluated here start in the 3rd decade of life, and we've got quite a few patients that are near that point or in that point. They have many, many different kinds of anticonvulsant medication. It's a cocktail of anticonvulsant medication because they are having seizures that are drug resistant. And their epileptic foci were in different places here. And then this is a state trait anxiety index score, and these are all within the normal range. So that's the characteristics of our patients. Where were the electrodes? And this, of course, is always a challenge to pull out. But what I'm showing you here in this figure, which Mariana generated so skillfully, are the 11 patients, and color-coded. You can see the individual electrode positions in the patients. Now, of course, you can't see the whole array in one patient, but you can see that this confetti diagram, as I like to call it, shows that these posterior, inferior and posterior occipitotemporal regions are covered quite well. What we then did was, to try and make this problem manageable and tangible, because when you deal with a plot like this, how do you start to organize the data? We decided we would divide the data into 4 regions of interest. One was in the that we designated the inferior occipital cortex, and that's the most posterior, and you see that here in the diagram. The second was the fusiform cortex, and that's the most inferior here. That's represented there and there. And then the next one was the inferior temporal cortex, which is just dorsal to that. And finally, the superior temporal cortex, which of course is the most dorsal there. Now, we had other electrode sites in other places that we wanted to investigate, but there were not enough contacts to actually do proper analyses on. And so that is why our investigation is really focused on these 4 regions of interest. These are the number of electrode contacts that are on each of the regions. Okay, so what did we find? Now, I warn you, these are going to be very busy slides, but I'm going to take you through them slowly. Let's talk about responsivity, 2 faces first. And this diagram here at the bottom of the figure here on the left side just shows you those 4 regions of interest I talked about. And this is a MNI, a 3-dimensional space coordinate in the MNI coordinate space that depicts the Y coordinate, which is this coordinate that goes from front to back, with negative being the most posterior. Now, where did I lose my mouse? The negative being the most posterior here, which of course is the inferior occipital cortex. And this just shows you the spread of where the electrodes were across these long structures here. As you can see on fusiform cortex, we've got quite a sampling in the anterior posterior direction. Okay, so that's where the electrodes were. We divided the activity up into categories. Contacts that were gray were unresponsive. You don't see them so well here on the diagram, and that's because you shouldn't, because they're unresponsive. What we're interested in is the response to phase 1 only, the response to phase 1 and 2, and the response to phase 2 only. And so those are color-coded here. It's hard to see those, of course, with this kind of display, hard to get a numerical assessment of it. But what we've done here is grouped them according to this posterior Y coordinate here, so that you can see the distribution in the individual subjects, okay? In these individual contacts, you can see where these are. What we've also done here is we've categorized the sites again with the same color coding. And now you see the proportion of responsivity to a particular stimulus type. And what I want to draw your attention to is that, say in the fusiform cortex, it's not so responsive to the emotional face and the face with the change in social direction, not to the dynamic face, as we call it. And that's what I'm going to call it, for a lack of a better word, from now on. But in the superior temporal cortex, you get and also in the inferior temporal cortex and superior temporal cortex and inferior temporal cortex, you get the proportion changes. The proportions change through here. I'm sorry, I misspoke. This was inferior occipital cortex. The proportion changes through here. This was fusiform cortex, and this is the response to phase 1 and phase 1 and 2. And then when you look at the proportion, this STS, the superior temporal cortex, responds more to the moving faces. And I'll show you that in a moment a bit more clearly when we look at the responses themselves. So, as I said, complicated data set. We're trying to make it manageable. So there's a hint here that there might be something interesting in the data. Let's talk through this slowly. This is, if we look down the bottom here, this is just representing schematically the regions of interest, the inferior occipital cortex, the superior temporal, the inferior temporal, and the fusiform. You see this funny looking shading here in these three things. This shading here reflects the area that we are depicting here, that I'm showing you the responses from. So it's a slice.
A quick question.
Yes.
What is the activity? Is it a high frequency power? Is it evoked response?
Thank you, Rafi, for asking. These are going to be field potentials. And they're
but what aspect of the field potential is it? Do you take the powers? I mean, do you take the high frequency broadband?
This
just
is
evoked
not,
response.
It's just the evoked response,
okay.
0.1 to 40 hertz, Rafi.
Okay, thank you.
Yeah, thank you, and thank you for interrupting me, because I want this to be clear. Okay, so we've taken that activity from a slab, this slab of cortex here, and this is just showing you what this looks like across these slices at these various regions of interest. And you can, and the way this is depicted is that phase 1 is depicted in blue, the response, and the response to phase 2 is depicted in red. And there are confidence intervals around each of these plots. So you see. So the point here of this slide is to show you that it is actually, the activity can be quite variable, and it's hard to make sense of it. And that's why it's very difficult to work with intracranial recordings. What this shows you here are the averages of the activity for the 4 sites. And you can see that there are, quite interesting latency differences between these. And this is the phase 1 response. There's a lag here in activity in the superior temporal cortex relative to these other ones, which respond to the onset of a static face. When there's a change to the face, where there's a change in direction of gaze, social attention, and also emotion, that superior temporal cortical response the latency changes quite radically. And you can see that in this plot here. Let me take you through this plot here. This is the peak latency for phase 1 and 2 across the 4 regions of interest. And for all of these 3 regions of interest, there's a significant difference in the latencies, the peak latencies. The phase 1 latencies are earlier. If you show it the dynamic phase, the response is longer, but the opposite occurs in the superior temporal cortex. Here, the latency shortens relative to everything else. And then if you look at the amplitude here, this is just an amplitude effect, which I'm going to pull apart in a moment. And these are absolute Cohens D effects. And this is what I'd like to pull apart now. This is the Cohens D plotted here for each of the 4 regions of interest. And you can see the electrode sites that are included here. And we have now split out the emotion and the gaze part of that stimulus transition in phase 2. And what I want to draw your attention to is that in the superior temporal cortex, there is a really quite large response to the gaze. And these black circles reflect mean values. So this is a very, very robust response to gaze in the superior temporal cortex. And I'll show you what that looks like in a minute. We'll zone in on that. And then here are the other effects that are not significantly different when you test for the size of these effects across the other regions of interest. It's only in the superior temporal cortex that across emotion and gaze, you get a very, very different effect size. So just to show you what the activity looks like, this is the STS. And these are all the sites that we had in the STS. This is the left hemisphere. This is the right hemisphere. The patient number is reflected and the electrode sites and where the MNI coordinate is. What I want to draw your attention to is that the direct gaze plot is the one in red, always. The averted gaze is the one in orange. And then we've got the statistical tests I told you about, looking at when the activity is significant across time. And of course, this is the average. I'm not showing you the confidence intervals here, which I showed you earlier. But this shows you where the activity is significant. So the bottom line here is that in this STC region of interest, which was mainly in the STS, there's a very strong preference for gaze aversion. Now, that's not particularly surprising because we've demonstrated that in non-invasive recordings. The question was then, when we saw that in non-invasive recordings, well, where's that activity coming from? So we think it's really coming from the STS itself. Okay, so one last thing to just show to you is that on this aspect is that, and this is in one particular patient. So here are the 4 regions of interest in one particular patient. This is the STS activity that I showed you just on the previous slide for this patient. And you can see where those electrodes are. This is the activity to the emotional part of the face that's pulled out. And that doesn't differentiate when you look at when the happy or the fearful face is presented. That does not differentiate in the way that the gaze does. So that's why we're claiming that there's a sensitivity to gaze here in the superior temporal cortical ROI, which is really in the STS. And then in the fusiform, of course, contrast that to the fusiform. Here's the gaze thing. There's no real difference here. If anything, if there's going to be something, it's going to probably be a bit more related to the emotion of the face, and then the inferior occipital cortex, which is the most posterior, is has a little bit of both, and the inferior temporal cortex, it doesn't really differentiate either. So these two don't differentiate so much so, but the thing that really stands out is the STS. Okay, so then how do we relate that to where the white matter pathways might be, and how might that information travel along the hierarchy, if you will? And this is now I turn to the work of Dan Bullock, who's pictured here, and this is Franco Pestilli. And now Dan was working with the Human Connectome Project MRI data set. And so what he's done is he's developed a method to statistically track where these tracts start and end. And I'm picking on one particular tract here. There is its starting point, here is its ending point. What he does is he goes through in individual subjects and runs his routine, which, as I said, is based on both gray and white matter anatomy, and generates just a voxel kind of mask where if there's a tract endpoint for any of these tracts, he'll generate a mask which will have a value of 1. It'll be 0 if a particular voxel doesn't contain a tract endpoint. And then he does this for over 1,000 subjects. He did it for 1,066 subjects of the Human Connectome that had good good quality diffusion weighted imaging data. And so then he just takes all of those individual subjects data and just sums those voxel masks. And then you get a quasi-statistical distribution, because the ones that are have the darkest colors have the most number of subjects endpoints in a particular position. So the colors at this end indicate that more individuals have a particular tract endpoint in that location. So I hope that explains that. And so then we took data from those posterior tracts that I showed you very, very early in my talk, and then just basically did an overlap analysis. Said, okay, is there an active neurophysiological site at a point where in another data set, now this is Human Connectome and this is the patients, but they're all in the same 3D space, okay? So we just asked, is there a match between the tract endpoint and where there's an active site? And so then we did an overlap analysis where these are the regions of interest and the responses to phase 1 and 2. We also included the IPS in here because we had a few electrode sites. We just did that for just to see. And then we plot the tracts and their endpoints. And then this color scale reflects the proportion of EEG sites in the termination area. And then looking at where there's an active site at one tract endpoint, we look to see whether there's overlap at the other endpoint. And in this way, we try to work out how the information might flow between in the system. And so what we did was, this is what we came up with as a schema for potentially for how the information might flow between the various structures in this task, in these 11 people. So we all start off at the inferior occipital cortex. It has the earliest latencies typically. And then we think the information travels to the inferior temporal cortex via the inferior longitudinal fasciculus. And then via the posterior arcuate fasciculus, posterior aspect of the arcuate fasciculus, we think the ITC then sends its information to the superior temporal cortex and the fusiform. And that's kind of our working model right now. And there are a few other connections that we didn't have enough electrodes on that we think. I mean, these are small numbers anyway that I'm talking about here. But this is our working model, which, you know, can be tested, was our working model that could be tested. We don't claim that it's definitive by any means, but it's just something to think about and to work on. As we so that's really the summary of what we did here with these two analyses. Let me just summarize really quickly, and then I want to turn very briefly to outstanding questions before I finish. Okay, so we're using the latencies of evoked IEG or intracranial activity. We think this underutilized for studying how information is transferred in the phase processing system. We have tried to link neurophysiology and white matter tract endpoints because we think it might offer another way to study information flow in the system, in the brain's information processing systems. And we think that the IOC and the ITC, they're very important components of the core and extended systems, and they haven't really been given so much attention. Now, the inferior occipital cortex, specifically the inferior occipital gyrus, Jim Haxby proposed that as being probably a critical starting point for the face processing system. And so I think based on this data set, I think, you know, that was the right conclusion. Our data are consistent with that for sure. But I think the Cinderella of the system is the inferior temporal cortex, because it's potentially performing an important function. It's providing information to the STS and to the fusiform gyrus. And the question is, what else is it doing? Is it doing some sort of differentiation? We can't see it neurophysiologically. But, you know, what is the nature of the link between that cortex and respectively the STS and the fusiform? So that's where I think is an important area for future studies, to try and pull apart these kinds of potential pathways. So as I'm finishing up, I want to turn to outstanding questions. Because as we were doing the second revision of this study for cerebral cortex, this came out. This paper came out. This important paper, which came out from David Pitcher and Leslie Ungerleider about the third visual pathway. And Jim, of course, mentioned this last week. And so, you know, I had been talking to you about this kind of approach with dorsal ventral pathways, and you know, and of course where the STS sits. And we always thought that the STS might be a kind of a important point of integration between the two pathways. That's how I've always thought about things. So it was really surprising to me to read this paper, and gratifying actually in many ways, because there are two things that have bugged me for about 20 years now, and I want to tell you about them real quick before I finish. That relates to the three of these, which of course we didn't think about this pathway in this way earlier. But let me just briefly mention them. Way back in the late 90s, we published a fMRI study with looking at all sorts of facial movements, eyes moving right and left relative to a face that's directing its gaze at you. We moved the mouths of these faces as well. We did both. And then we had these simulated eyes and mouth conditions where we had these checkerboards that moved in the same spatial positions as the facial features that were being moved. And then we had another condition where the face remained completely still, and this pattern of rings moved inward. And the idea here was, at the time we knew about MTV5 and its sensitivity to motion. And so what we were trying to do here was we were trying to separate that out from these movements of stimuli that were non-face-like versus facial motion. And it was done in a block design. Okay, so one condition versus another, like so. And this is what we got for the various conditions. The bottom line was the STS was responsive to the face, moving face parts, and not so to the other moving stimuli. But then everything posteriorly activated in MTV5 to all of the stimulus types. Now, yes, when you looked at the actual activation profiles, which I'm not showing you here, they were larger to the faces. And at the time, I just thought, well, it's probably an emotion, an attention effect, the stimuli more salient. Maybe that's what's causing this sort of increased gain in the system. Okay, but I could never make sense of it. But when we think about it in terms of the third pathway, this is consistent with that. Then collaborators in Japan took our stimuli from that task. We had 2 stimulus faces. This is what I looked like a million years ago. And we did an experiment with the eye part of the stimulus. So here's the real eye gaze thing, and it's just the eyes shifting backward and forward, the simulated cheeks moving backward and forward, and then a still face with the radial background moving in. And this is work I did in with Riki Kakigi, and Shoko Watanabe did all the hard work here. They had a 37 channel system, MEG system back then. This was, the early 2000s, which covered the posterior brain. And so the idea was we were particularly interested in looking at this transition between S1 and S2, and shown here. And so here is just a plot of all of the activity. And then here, we've just equated the pre-stimulus baseline so that we can take measurements for this stimulus. And here, to make a measurement for the second stimulus, we have taken, again, the baseline there. So it just shows you that there is responsivity to that second phase. And so when we actually look at where the source models are for that activity, this is one of the subjects. So here's the real eyes, here are the simulated eyes, and then the radial pattern stimulus. They all give nice, robust responses. And then when we localize them to the region, and these are the dipoles as shown here, when we plot them on a 3-dimensional space, they're all in the same location. So here's MTV5 as a source for this activity, and that's what we published at the time. And of course, the array was too far back to record activity in the STS, so we could never see the activity in the STS. But that said, MTV5 was really had its own focus of activity, and so those 2 observations, I've always had those in my head. And so in terms of the context of this work, are we seeing activity that's really MTV5 in this data set that I've analyzed? And I'll be interested to see what Rafi has to say about this. But are we actually seeing MTV5 here? Now, of course, we don't know because we didn't actually test and do motion controls in this task. But what I'd like to advocate as I finish up now is the need for using dynamic stimuli for studying both expression and identity, because now we have a conundrum, because we have a whole lot of work based on static faces and then some work on mobile faces. And I think it's hard to put these two together, but this might be equivalent. And that's the outstanding question I want to leave you with. So thank you for listening. Let me stop my share.
Thank you, Aina, very much. This was a really interesting talk and very thorough. And I want to ask everybody to unmute yourself so we can give Aina a very big applaud. Really, really interesting. And okay, Rafi, there are some questions directly related to you, so you start.
So thanks, very interesting, and as usual, really powerful study. My two comments, sort of technical, but I think they're relevant. One is to your directly thinking how to answer your question, whether it's MTV5 or something else. It occurred to me that you might have in the transition between phase 1 and phase 2 some motion, and that, you know, it might be different between different stimuli, but you can do some kind of a Euclidean distance measure, pick up those that move more and see and use that as a sort of control, simply because, yeah, this is the situation. And that's one. The second one, which is more interesting to me, is, you know, you can use a completely different way to characterize connectivity, and that is by using what's called functional connectivity. In other words, look for correlation in the dynamics of the signal, but outside of the stimulus. You know, during the stimulus, of course, we have all this bottom up, but maybe in a sort of rest before the stimulus or after or in times, it will be interesting to see whether your contacts show a correlation that might be related to these pathways that you see indirectly, and that will be a way to combine, you know, different. So I wonder whether you have any looked up at that analysis of that.
No, we haven't, but it's something that I certainly have had in my mind, and looking at something like maybe a power envelope correlation or something along those lines, or you know, measures like I thought about measures like imaginary coherence and other things like along those lines as well.
Also to look at the power of high frequency, not only the evoked response.
Exactly. So yes, I have been thinking about those kinds of things. The reason we didn't do that, because we thought about that originally, was we still feel a bit funny about the epileptic activity. We tried to kick out the epileptic activity, and so we didn't focus on the high frequency stuff because we didn't trust that part of the data. And so that's what's so, for me, unsatisfying about doing all of this work. Because we didn't trust. Yeah.
But if you get a very neat and clean result, it will be difficult to, so you can use that as an argument.
Yeah, no, I agree.
I believe in, you know, and using dirty data if it shows nice results. I mean, if it really shows consistent, clean, you know, not if it shows something crazy, but if it looks compatible.
Yeah, but that's a good suggestion. That's a good suggestion. I knew that I could get a good suggestion from you, but I think so the question is, okay, let me put a question to you.
Okay.
Do you buy the argument about the IOG and the equivalence that I'm proposing of the IOG and the MTV5 here?
It's possible. I mean, I believe in, you know, in a specialization that a very fine grain. So I will not be surprised if what we tended to call at the time MTV5 in general will be subdivided into different functions, and how they fit into networks. It's your job. You have the data. You can do it. I mean, you can do the analysis and see if there is a for example, find whether there is a correlation within the MTV5 between different contacts, you know, within the one patient, of course. You don't do it across patients.
Right.
And then I think this is a beautifully powerful potential data set to analyze.
Yeah, there's only one problem, that, you know, you know the anatomy of MTV5 better than anyone in the world, probably. you know that it's highly folded cortex. And neurosurgeons don't really like to go near stuff like that because then they can damage things. So that's why we've got a problem.
Yeah, okay. But still, you have a lot of contacts, and you could sort of
yeah. No, that's and that's something that we can explore as we go further. So thank you for your comments.
Thank you.
Insightful as always.
Aina, I want to ask, I mean, I know that the resolution, the spatial resolution, or the, let's say, anatomical resolution may not be sufficient according to the context that you have, but basically MT is supposed to have retinopathy. So in the motion that you're describing may have some, so I don't know what was the visual angle, how big the stimulus was and whether, but certainly the motion in the eyes may not be the same as the radial motion that you describe, or if you see some consistency, so I don't know if the resolution, like how many, like within a specific person, do you have several electrodes that you classify as IOG, or?
I'd have to have a specific look, Sharon, but I think I think the quick answer to your point is unfortunately no, because typically the spacing and these are depth probes, and the spacing between electrodes is well, at least the centers of the electrodes is sometimes it's 10 millimeters, sometimes it's 5 millimeters. Okay. So even with the 5 millimeters, it's a tricky one. Now, Vadim was mentioning that he had some data with multi-unit activity from that same epilepsy center. I would say, Vadim, you should look there in the multi-unit activity and to see whether you can, differentiate things further. There, Sharon, if it depends on, of course, because the multi-unit activity there's just a set of wires dangling at the top end of the probe, and the positioning of those is the neurosurgeon just turning the probe outside of the head, and that's the position. So you take what you can get. But I mean, Vadim, do you want to make a comment about that?
And in multi-unit, you have also the problem of localization. In LFP, you'll just look in anatomical location on the CT and the MRI, and you can know exactly where was the contact. In multi-units, you need to look at the CT image, and still you don't know exactly which wire it was. And they can be quite long. For example, in my case, I was not even sure whether it's in the FFA or not, because I overlapped the wire and overlapped the activation, but I was not sure whether it's the wire which responded. There are 8 wires in the freed electrodes, so you never know.
Thank you for clarifying that, and how challenging it is to do multi-unit studies. And in fact, that's where I think we need to, why I would send a stimulus out to people to think about doing really detailed studies of functional connectivity, perhaps in healthy subjects, and doing it in source space, for neurophysiological studies, in non-invasive studies in source space, because we need to disentangle these relationships, because there are limits. Everyone says, oh, it's the gold standard, the intracranial electrophysiology. It's not, because we have challenges, as Vadim said, with multi-unit, and as I've pointed out, many limitations with the intracranial work that I presented today.
Question.
Go ahead.
Related to what Rafi asked you during the talk, that you used the evoked potentials and not gamma power, high gamma power,
exactly.
Like Rafi used in his studies. So the question is, usually people, at least like they cite following the Rafi work with Remo Kamel, that high power is more related to fMRI activity. And on one hand, on the other hand, so So how it's related? So there was a paper about 10 years ago of Jean-Philippe Lachaud in which he compared the high power, not high power. So there are regions which are active for both, for one of them. So how you suggest to make sense of this mess? Which of them is right?
It's a mess. That's exactly right. But that's why we originally, Vadim, had proposed to break down our activity in alpha, beta, and gamma, and then we didn't trust the gamma stuff because of the epileptic, activity. These patients had really. I think what we would need is we would need to do this properly in future would be to do a proper task which was focused at answering this kind of question, and then just collecting a much larger set of patients than what we had. Because look, we 18 is not much. It sounds like it's a lot of subjects, but in that last study, that proper study that we did with Truett and Greg, we had almost 100 patients. Okay, so we need the numbers because they all have different samplings, and you're going to throw out a lot of data that's epileptogenic, and that's all in the gamma band, and we didn't trust it.
And there are few phase selective electrodes anyway. In each subject,
exactly.
The chances to fall upon phase selective contact is not high.
You're absolutely right, Vadim, and so we're conservative in the sense that we realize we actually wanted to do all this, modern functional connectivity. But if you don't trust your data, then if we would have got measurements, I mean, as Rafi makes a point, okay, it's dirty data. If you get what you want, you're okay. But what if you...
Well, not what you want, but consistent, reproducible.
Oh my goodness, I knew I'd get a reaction. I love it. But I mean, you made a good point, Rafi, about trying, but we didn't, because we didn't believe that we could maybe demonstrate what we were going to try and demonstrate. And so that's why we thought, let's be conservative. Now, Vadim makes a really important point. We've looked at activity in mainly the alpha beta range delta. There could be a completely different story in the gamma. No, I take that point. Absolutely.
I want to ask about that. I mean, if you've got connectivity, I mean, I know that during epileptic seizures, everything starts to be connected. But what if, wouldn't areas that are consistently connected during task be more connected? I mean, could you regress out the whole, the overall connectivity? I mean, would you see any delta? Any additional connectivity of regions that are really part of the same network, or is everything I'm asking, epileptic?
I don't know is the answer, but what I can say is that my colleague Rick Betzel, working with Danny Bassett, looked at some connectivity measures in epilepsy patients, and using the kind of normal regular approach, and they claim to get things. Now I asked them, how did you control for epileptic activity? So and they assumed that the data sets that they had got had been cleaned of that. So I think what you're bringing up is a very important point, Sharon, that there's two ways to go, taking and synthesizing everything that's been discussed so far. We can either attempt valiantly to study the pathways of face processing directly, and then we end up running into all of those problems that Vadim and Rafi and I have mentioned. Or we can take the bull by the horns and look at epileptogenic activity itself as a vehicle for transmission. Now, I'm not making a new idea. People like my department chair at Yale, when I was at Yale, Dennis Spencer and Susan Spencer, his life partner and also scientific partner, were doing that way back then. But they didn't have the methods that we have now to do that. So that is how I would tackle that question.
And you're almost going to double your data. I mean, it sounds like, for this purpose.
Yeah.
And
but you still run into the same problem as Vadim said. You have to take what you can get with the electrodes, right? They're not going to be necessarily in the locations that you want them to be.
Yeah,
and that's the
exactly.
frustrating part. And Vadim, you know that sometimes even with if you're working with grids that are on the surface, subdural arrays, and you get an effect and it's right on the edge of the grid and you can't see what's next to it because there's nothing, there are no contacts. And that's just one of the really frustrating things of working with intracranial electrophysiology. And I don't do that anymore, and I'm really glad I don't. And this exercise in studying these data it just brought back all of those challenges again.
At least with the grid, you have a large coverage. When we have the depth electrodes, like in Paris, the coverage is, and each subject is not completely, but you don't have two subjects with the same content.
Yeah, well, we did and you're right. And so we did we had both. We had the depth and we had the subdural. Yeah.
Oh, wow.
No, I know what you mean.
But just to add some optimistic, I mean, I think the intracranial is not so much worse than doing diffusion tensor imaging, which has a lot of problems on its own. So the beauty here is to combine them. In other words, each one suffers from some dreadful problems, but maybe when you combine them, you get something much cleaner, much more consistent.
Yeah, you're an optimist.
Diffusion tensor imaging has a lot of problems. I mean, we need to...
crossing fibers and interpretations.
The crossing fibers is the thing. And so that is why this approach of bands with using, specialized imaging sequences and also taking into account other anatomical landmarks in the gray matter. Now, I'm not saying what he did was definitive, but it's an improvement on what we have. And Rafi is absolutely right. And I think the only way to do and make it better is to do at high field strength 7 Tesla, specialized imaging sequences that are specially designed to deal with the crossing fiber problem. And so we, of course, did, we were optimists, actually, Rafi. We decided we could take DWI data and intracranial data and do something with it. So I'm not a pessimist. I am an optimist. I just have a bit of a pessimistic outlook on what we ended up with.
But it's very, very, very nice study. Very interesting.
Yeah, I think it has great potential. I will insist on combining functional connectivity to that. Despite all the misgivings and all the problems, which are of course correct, but still there is a lot of rich data potentiality there that I will not throw away by no means.
I agree.
Yeah, all these causal methods with the intracranial and electrophysiology might be more robust than with fMRI. Like the DCM with the fMRI is there some concern because of ball delay.
Yeah. And the nice part about neurophysiology is you've got millisecond by millisecond latency differences, and that's where I think the power lies. But I mean, what does Galia or Nicholas think? Because they've been sitting here listening. What are their opinions?
Galia, Nicholas, do you want to comment? While they are unmuting themselves, I would also like to say that if this is MT, you would expect very short latencies in the response relative to SDS. So even earlier than like 70 milliseconds or something like that. So you can have a look at because if it's something to do with the face network and it's specific to faces, or it's very likely to be later on. MTs, latencies are, so that's something that you may have a look at, the actual latencies of the responses, and not just the amplitude or the anatomical location. And it would not show specificity, I mean, to faces. Usually it's just, you know, motion in specific spatial locations would activate it.
You know, what's interesting about that, Sharon, is that when we first did that non-invasively and we started working with motion, the kinds of responses we got were a lot slower than to that onset where you're really blasting the visual cortex. So that's other work that has to be done. So we're identifying work that has to be done. Gal, you're unmuted for that microsecond.
Yeah, he was unmuted for a bit.
No, I'm here. I'm listening to this interesting conversation, but yeah, I think, I mean, everything has been said already. I thought, I mean, my response was similar to what Sharon just mentioned about latencies and how you probably would expect to see earlier latencies in areas such as MT, and that's going to be different from face-related areas. And of course, there's functional connectivity. It's hard to talk about latencies. It's really not the best tool for that, or, you know, we don't have that.
Well, there are things like transfer entropy, but every time I've tried to talk to people about that, they go and run and hide under desks because it's really complicated. But I think that's the way it goes.
It's super complicated, and it's really sort of, it's a statistical model rather than being, you know, real recordings with latencies that are actually sort of meaning from the data itself. So I don't know. I mean, when I think about functional connectivity, it's hard for me to think about latencies. I think it's just not a good.
Just to add support to what Galia said, I don't trust causality delays, because there are delays that are local, not related to connectivity. But I do trust functional connectivity as a tool to say the two places are connected. Whether one is driving the other or not, that's a different issue. But connectivity is more, again, it has problems, zillions of problems.
Right.
But
Absolutely.
at least it's more.
It's meaningful in the sense that you mentioned, Rafa, just to sort of indicate that there is relation or some connectivity, maybe not direct, but some connectivity between the regions. But I also find the temporal analysis of functional connectivity kind of, I don't think about it as sort of a reliable way to look at temporal dynamics, and you have intracranial recordings, so that's much better.
Aina, thank you very much for sharing with us this, well, I find it really exciting and informative data. And I do hope that you or some other students or collaborators will follow up on that. It's really exciting. And thank you very much, and happy winter holidays that are coming your way, and happy winter holidays to everybody. And we will take a break. We will be here on January 10th. So thank you very much for joining us again.
It was wonderful.
Thank you.
Seeing you.
Thank you.
Take care.
Thank you. Thank you.
Bye.
Bye.
Bye.